Hello, this is Dr. Muhammad, and this is another video under design of steel structures according to AISC. And today we're going to talk about beams part 2. And in today's video, I'm going to talk about several topics. The first one is related to the global instability, and the second is regarding local instability. And then I'm going to talk about the classification of shapes, compact, non-compact, and slender. And then I'm going to discuss about the bending strength of compact shapes. And at the end, I'm going to give an example on this. So let's start with the first part, which is related to the global instability. Okay, so regarding global instability, whenever that we have a beam, as you can see here, and this beam bends, the compression region of the flange above the neutral axis, if we say this is here, neutral axis, the compression part is going to this part, which is, you can see it here in this figure. Okay, you're going to find that this part is going to be under compression. So this means that we have like a T-shape that is working as a compression member, like a column, and it is under compressive forces. This means that it is going, or it tends to buckle. Okay, so when a beam bends, the compression region above the neutral axis, as I said, this is the neutral axis, and above it, it is where we are expecting the compression region, is analogous to a column, and in a manner similar to a column, it will buckle if the member is slender enough. So it is going to buckle. Let's have a look on this figure here. This is the elevation or side view of the beam, and this is the top view. Whenever that we are loading the beam in this direction, we're going to find that the beam bends in flexure mode, as you can see here from the side view. But when you look from above, from a top view, you're going to find that the beam is going to laterally move. So this point, which is point B, it is going to move, okay, to laterally in this direction. So this is what we call it, lateral deflection of the compression flange. Lateral deflection of the compression flange. So this part is not going only to buckle, it is going to laterally buckle. Okay, it's not going to buckle, I mean that in the maintaining the same position. No, it is going to laterally move. Okay, laterally moves, and in the same time it is going to have a torsional or twisting, okay, twisting motion, as you can see here and as you can see here. So this is the compression flange. This is the compression flange, and you are going to find that this compression flange moves laterally, which is here, as we said, it moves laterally, and in the same time there is rotation. This point A, moves here, and point B moves here. Okay, so this is what we call it global instability. Under the flexural or under vertical loading of the beam is going to laterally move, and in the same time it is going to twist around like an axis. It is going to twist, laterally moves and twist. Okay, so this is what we call it the global instability. Okay, the difference between what we were discussing before and regarding the compression member and the column, and when we compare them with the beam, or what is going to happen for the global instability of the beam, that the compression portion of the cross section is restrained by the tension portion. So the remaining part here, the remaining part of the cross section, it is under tension. It is under tension. So it starts to restrain this part from going laterally. Okay, and the outward deflection, which is the flexural buckling, is accompanied by twisting torsion motion. This means that this part, which is the compression part, it is going to buckle, okay, in this direction. But because there is tension portion here, it is this part of the cross section, it is going to be under tension. So it is going to restrain this part from, or the compression part from going laterally. Based on that, you are going to find this part is behaving as if it goes laterally and twist in the same time. So it gives us this this motion. Okay. Okay. So now let's go and understand more about this. This global instability phenomenon, we call it lateral torsional buckling, LTB. Lateral, we understood why we call it lateral, because of the lateral movement. Torsional, we understood now why there is torsional part is going to control or going to be part of the motion, because of the tension part, as I said. It is going to restrain this compression part from going laterally without like twisting. Okay, so this is going to like make this compression part to twist in the same time. Okay, anyway, the discussion from this slide is going to give us something that is very important for understanding the beam behavior or steel beam behavior. We call it LTB, lateral torsional buckling. It is a phenomenon that is related to the global instability of the beam. And whenever you look to it, you're going to find that there is lateral buckling that is going to take place due to the compression part or the compression portion of the beam, and there is kind of torsion that is going to be there because of the contribution of the tension part of the beam. Okay, the tension part would not buckle and would not twist, but the point is it is going to restrain the bottom of the compression member or the compression part. Then this flange is going to be like this, as we said, it is going to move in this way. So the solid black part here is going to like move in this way, laterally, and making this twisting motion. Okay, so this is the composition of these two parts, okay, lateral buckling and torsion. Okay. Okay, so if we have this idea now that of the instability as we have discussed in the previous slide, this means that we need to stabilize this lateral torsional buckling phenomena. Okay, so we need to stabilize it. So we need to discuss about the stability of this lateral torsional buckling. Okay, so for the stability, we have like two different types of bracing. Okay, so we are having like two different bracing types that is going to stabilize or like work against the lateral torsional buckling phenomena. Okay, the first type of bracing, we call it stability bracing, and the second we call it torsional bracing. Stability bracing and torsional bracing. In stability bracing, we are going to look to the part that is going to be under compression, which is the part that is above the neutral axis. Commonly in I shapes, this is the flange, the top flange. So if we could restrain the top flange or the compression flange from going laterally by providing some bracings, for example, if we have a plan like this, okay, and we are having like the beams, okay, running in this direction. So this means that we can provide some like lateral bracing. This lateral bracing is going to be in the level or at the level of compression flange. So it is going to restrain the compression flange from going laterally. Okay, so this is what we call it stability bracing. And this is commonly we put it in the plane of the compression flange. This is a plan, if we're talking about the plan view of a floor, for example. Okay, so this is what we call it stability bracing. Take care of one thing that we are talking always here related to the compression flange, okay, not tension flange. Okay, That's very important. Okay. The second part, or the second type of the stability bracing, we call it not the second type of bracing, we call it torsional bracing. Torsional bracing. In this torsional bracing, we are going to provide diaphragm or cross frame, as you can see, which is going to control, as you can see here, this part of the web is going to be restrained. Actually, most of the web part is going to be restrained, but we are concerned with the part that is related to the compression flange. So we're going to control this torsional, or we are going to control the compression flange lateral movement and torsional or twisting behavior by stabilizing the web itself by providing a diaphragm or cross frame. Cross frame means that if we have like plate girder or I section here, we can put and provide some elements. They are going to stabilize the web and the flange. Okay, remember that this part, which is this part of the web, is considered to be very important in stabilizing the flange itself. If we could stabilize this part, okay, like the neck, if we say that this is the if this is the flange, for example, here, okay, and here this part, which is directly underneath the flange, this neck, if we could control it, then the flange would not go laterally, okay, or will not twist after that. Okay, so this is the two types of bracings, or two types of bracing that we can use to resist lateral torsional buckling. Okay, and lateral torsional buckling can be prevented by bracing beam against twisting at sufficient close intervals. And we said that this is like the intervals here. We can control it like this. Okay. And only one hint that is important related to each type of bracing. For the stability bracing, lateral bracing, which prevents lateral translation, should be applied as close to the compression flange as possible. In this case, it is not right to put any bracing on the tension flange or in the middle part, for example, of the web. This would not work for us, but stability bracing should always be close to the compression flange. And for the case of torsional bracing, it prevents twist directly. As you can see, this is very effective in preventing twisting, right? It can be either nodal or continuous, and it can take the form of either cross frames or diaphragms. Means that you are we have two types here, nodal or continuous, and cross frame something like this, or diaphragm something like this. Okay, that is like something nodal, that is we can control the along the cross section itself. If we have the cross section, for example, if this is the cross section and this is the the flange here and the web, we can control this by putting something laterally. Okay, we can put something laterally here. So this is something like this, and at another interval we are going to put something like lateral, like this, if it is cross bracing or anything that is going to control, okay, control the flange that we are concerned with. Okay, so this is what or how we can control the instability due to lateral torsional buckling. Okay, there is other types of definite lateral support that we can do in order to prevent the lateral torsional buckling for the compression flange. First of all, the flange can be embedded in a concrete slab, or we can use shear studs or shear connectors. So this is the compression flange. So we are guaranteeing here that there is no movement at all from the compression flange because it is embedded in concrete slab or connected to the concrete slab through shear connections. And some other types is something like this, if we have a deck, metal deck, for example, here, then we're going to like make the connection of the girders or the beams to the secondary beams to the girders near to the top, which is near to the compression flange. As you can see, this would be a very good restraint against any lateral movement and lateral torsional buckling. In a similar way, if we have an open web joist deck, so we are going to have that connected at the top here. So this would make a prevention through welding to any kind of lateral movement of the compression flange. Similar way, if we have something like I section, then we are having different angles controlling the compression flange. If we are going to connect secondary beam like channel strut, for example, and it is going to be at this level, which is the level of the web away from the flange, then we need to use stiffener. Okay, we need to use stiffener. So this stiffener is going to control the lateral movement of the compression flange. Okay, so take care of this. It's different than this case. Here, this case, the secondary beam is close enough to the compression flange. Here, it is not. The channel strut is not close, so we need to use stiffeners. If we have a roof purlin, for example, and it is welded to the top flange of the I section, then it is going to be like a good restraint against lateral movement if we have a main roof beam or rigid frame section. Okay, this is like different types of lateral support of the compression flange to prevent lateral torsional buckling. Okay, now let's go to another case which is related to the local instability. Local instability. The meaning of local instability is that we are going to find under certain circumstances and conditions and loading conditions that the section is not going to globally buckle or twist like the lateral torsional buckling, but we're going to find that something local would happen. Whether it is in the flange, as you can see here, this is a very good example. Okay, we're going to find that there is like local buckling, flange local buckling here. Okay, as you can see here, this is flange local buckling. Or we are going to find it that is happening in the web itself. As you can see here, this is in the web. Even that there is some kink here, there is also like flange buckling, but we can see that this is also related to the web. Here, this is the web, and there is some buckling here. We call this local web buckling. Okay, so this is another type of local instability. We are facing different failure modes of beams whenever they are loaded under transverse loading. Okay, whether it is global or local. Okay, whether it is global or local. So here we were talking about something global, as we were discussing here. This is global. The whole entire section is going to move in this way. However, here we are talking about something local, whether in the flange or in the web. Okay, whether the beam can sustain a moment large enough to bring it to fully plastic condition also depends on whether cross-sectional integrity is maintained. That's right, because we are talking about local stuff here. This integrity will be lost if one of the compression elements of the cross-section buckles, whether it is the flange or the web. If the flange is going to buckle, we call it flange local buckling, FLB, as you can see it here. Okay. And if the compression part of the web is going to buckle, then we call it web local buckling, WLB, as you can see here. Okay, so how we can control this? We are going to control it based on, if we have this like web and flange, we are going to control it based on this two parts for the flange, which is T flange, or sorry, the width of the flange, okay, B flange over T flange. So B flange here, if we're talking about half of the width of the flange, so B flange over 2. Okay, so we are going to have like B flange over 2T flange, which is the width over the thickness, whether for the flange or for the beam or for the web, we are going to do the same. So width to thickness ratio of the compression elements of the cross section is going to be used for controlling this local instability. Okay, so now I'd like to recap what I've said. If we are having global, if we have global issues, global instability, which is lateral torsional buckling, then we can make these types of bracings or these kinds of bracing type, whether stability bracing or torsional bracing, by controlling the flange, compression flange. But if we are having some local issues, local instabilities, then whether in the flange, we call it flange local buckling, or in the web, we call it web local buckling, what should we do? Exactly, width to thickness ratio. We need to control, control width to thickness ratio. So if I ask you, at the end, what are the measures that you should do in order to restrain global instability? So number one is bracing, whether it is stability bracing or torsional bracing. However, the measures for resisting local instability is through width to thickness ratio control. This is what you should know. Okay. Now let's go to another part which is related to the classification of shapes. Classification of shapes. The classification of shapes is found in section B4 of the specification, which it is under the title of local buckling. You're going to find it in table B4.1. Stop the video and check your specification or your manual, chapter 16 for the specification. And you're going to find that related with local buckling, there are some parameters that you need to understand whenever that you're dealing with the classification of shapes, because they are going to be controlling parameters to judge your shape. What is the type of your shape? The point is, we have three different types of shapes. We call them compact, non-compact, and slender. And we are going to distinguish among these three types by using the parameter lambda. So lambda, it is the width thickness ratio, as we said before, whether for the flange or for the web. And there is going to be two main limits for us. We are going to have two main limits, and in between we are going to have compact, or non-compact, or slender. So we're going to have three areas with main two limits. The first limit is going to be lambda p, which is related to the plastic, for example, which is differentiating between compact and non-compact. And between non-compact and slender, we are going to put lambda r. So lambda p, we call it the upper limit for compact category, this is the upper limit here. And LR is the upper limit for non-compact category, which is LR here. After that, it is going to be slender. So this is how we are going to control the cross section and classify the shapes based on the width to thickness ratio. For the compact sections, lambda should always be less than or equal to lambda p. So there is no local buckling here. In this case, no local buckling. Do not care about the buckling of the cross section. No local. I'm talking about local. Still, we are under the measures for instability, but instability of local buckling, but we need to classify the elements first. For non-compact sections, commonly non-compact section means that our lambda is going to be between lambda p and lambda r. We call this inelastic local buckling. Take care of these wordings, okay? Inelastic local buckling. What is the meaning of this? This means that we are going to have some local buckling, but it is going to be inelastic. Some yielding of the material would be there. Okay? However, in the compact, it is going to be no local buckling at all. Here in the compact, we are expecting plastic moment. Okay? This means that we're going to exceed the yield even here. The non-compact, something in between. Okay, the fibers, some fibers are going to yield, but they are going to have and experience local, inelastic local buckling. For slender, we are going to experience local buckling only. There is no yield here. No fibers are going to experience F yield. Okay, so that's the three main categories. I'm going to explain more about them later. Note, the category is based on the worst width-thickness ratio of the cross-section. What is the meaning of this? For example, if we have like the web and two flanges, so we need to check for the flange and for the web as well. Okay, so if the flange is compact and the web is non-compact, then the entire section is going to be called non-compact. This is the meaning of worst. Okay, so the category is based on the worst width thickness ratio of the cross section. For example, if the web is compact and the flange is non-compact, the shape is classified as non-compact. Okay. Okay, this table has been extracted from AISC table B4.1. Please stop the video and check this table in your specification or in the manual, and is specialized for hot rolled eye-shaped cross sections. It is for eye sections, hot rolled. Okay, we're talking now all of our course based on hot rolled. Okay, plate girders or built-up members or girders, they are not our focus now. Later on, we're going to talk about those. Table 5.3 also applies to channels, except that lambda for flange is B flange over T flange. So also it applies to like channels. Okay. However, this is going to be B flange over T flange. Okay. However, here for our case for the section, this is going to be B flange over 2 flange. T flange. Okay, so this is the common thing whenever we're talking about the flanges. Okay, so this is lambda, and this is the upper limit for compact, and this is the upper limit for non-compact. This is R. I think it's related to the proportional limit, and P it is related to the plastic limit. Okay, I'm going to talk about this similar to. So we're going to have like three main regions here. Okay. So we're going to have, yes, these are the limits here. This is the region where that plastic is going to be there. So we're going to find L plastic, for example. Here it is going to be LR. R means that proportional limit that differentiates between elastic and inelastic. Elastic and inelastic regions. So buckling, elastic buckling and inelastic buckling. If we're talking about beams, so it is going to be elastic lateral torsional buckling and inelastic lateral torsional buckling. Here, this is the case of like full plastic model. It is the plastic modeling or plastic hinging, or we can call it the plastic moment would be developed here. Okay. Okay. For the web, we have the limits. It is going H over T web. So H, it is the height here over T web, width of the web itself. Our limiting values, as you can see, always we are having the radical of E over F yield in all of them. One interesting thing that whenever you compare the flange versus web, you're going to find the ratios or the values in general for the flanges are much less than those for webs. Okay, why? Why this point? Here 0.38 and here 1, here it is 3.75 and here 5.7, almost like 10 times here. Web is 10 times. So think about it. Think about it. and think about what is the main issue whenever that we're talking about flanges and webs. For the flange, it is stiffened from one part and free from the other part. For the web, it is stiffened from both ends, right? So this would be definitely reflected on the limits. So for the web, you are going to find it very high compared to the flange. This is the main reason, I think. Okay. Okay. Let's go to the next part, which is definition, which is an important definition for you. What is the meaning of compact, non-compact, and slender section? It's really important to know and to understand this. What I'm going to tell you in this video is very important for you whenever that you are designing, whether in design office or your own project. It is very important to understand what is the meaning of compact, because we are like using the definitions or using the terms, like stereotyping the terms without understanding what is the significance of them. Compact sections means that the section that can develop, take care of this, fully plastic moment, MP, before local buckling of any of its compression elements occurs. This means that the full cross section, okay, the full cross section is going to reach, okay, going to like reach the exceeds F yield before any of its compression part, whether the flange or web or whatever, buckles. This means that the section is going to work with me to develop MP. And I'm not concerned and I'm not worried about any buckling of any of its compression elements. However, for the non-compact section, I am going to expect that the section can develop a moment equal to or greater than M yield. So here, M yield is going to be developed. You're going to ask me what is the difference between MP and M yield. I'm going to show to you in a minute now, but remember that MP, it is like higher than M yield. Okay, I'm going to draw it. I'm going to draw it in a minute. Okay, maybe this is M yield, for example, here MP, plastic. We're going to find that the section can develop full plastic moment. Okay, do you remember the previous video? I was talking about the Z, the plastic section modulus, and we said that yielding, or we are going to reach the yielding of all the material or all the cross-section parts is going to yield, right? Then we are going to fully utilize the cross-section itself. However, in case of non-compact, the section can develop a moment equal to or greater than M yield, but less than MP, before local buckling of any of its element occurs. So part of the section is going to provide for us M yield, okay, and maybe a little bit excess, okay, some like more than M yield, but less than MP always. It is always less than MP. If we say, for example, MP is 120 and M yield is 100, okay, so the non-compact can provide, for example, 110, and after that, between 110, after 110, you're going to find what local buckling occurs. Compression flange would buckle, for example. Slender section is going to, local buckling occurs before M yield. So before any part of the cross-section yields, you're going to find that your section going to experience local buckling. One of its compression flange or web or whatever, it is going to buckle. Okay. Okay, now let's go to the bending strength of compact shapes. Bending strength of compact shapes. So bending strengths of compact shapes, a beam can fail by reaching MP and becoming fully plastic, or it can fail by the following. Okay, please go to the previous video to understand what is the meaning of MP. Okay, because I think that maybe you are confused, but already I have mentioned in the last video what is the meaning of MP and the difference between MP and M yield. Okay, MP over M yield, it is going to be, for most of the shapes that we are going to talk about, it is going to be larger than 1. Okay, so this means that in plastic the section can provide higher moment than the yield. Okay, if we maintain the section without local buckling. Okay, any of its parts would not experience local buckling. Okay, so for compact shapes, in case of compact shapes, so the beam can fail by reaching MP. This is the highest level of moment that it can resist, and becoming fully plastic, or can fail by other types, which is going to be, I think that the next one, I want to show you something. Okay, it is going to be here. Only I want you to know the names now, and I'm going to fully explain it for you in a minute. Lateral torsional buckling, we call it LTB, either elastically or inelastically, or flange local buckling, elastically or inelastically, okay, or web local buckling, elastically or inelastically. Okay, so we are talking about the compact shapes. Now we are talking about the beam in general. Okay, the beam in general can fall into this category. This is the general failure mode, all failure modes. If we are going to talk about compact section, then we are expecting to reach MP or lateral torsional buckling, okay, either elastically or inelastically. I'm going to talk about these two later. Okay. Okay, so we will begin with the compact shapes, defined as those whose whips are continuously connected to the flange and that satisfy the following width to thickness ratio. So why we need to width to thickness ratio? We want to be sure that there is no local buckling. And what is the meaning of continuously connected flange? This is the compression flange, because we are sure that there is no lateral buckling would happen to our cross section. Okay, so these are like two conditions here: continuously connected flange, okay, that the whips are continuously connected to the flange. Okay, that's an important issue. And the second is that the width to thickness ratio, okay, for the flanges and the whips are meeting these conditions: 0.38, the radical of E over F yield for the flange, and for the web it is going to be H over T web less than or equal to 3.76 times the radical. From where we got this? Go back to this table. Okay, this is lambda P, the upper limit for compact. Okay, so these are, you can find them from this table in the textbook or table B4.1, the specification. Okay, now for compact shapes, two failure modes are expected. Okay, now again, in order not to be confused, I was talking here about all the possible failure modes for beams. So it is going to be like reaching MP, or lateral torsional buckling, elastic or inelastic, or flange local buckling, elastic or inelastic, or web local buckling, elastic or inelastic. Now, for the compact shapes, we're talking about compact shapes, then we are going to have two failure modes are expected. We are going to reach MP and becoming fully plastic, so the entire section is going to be fully plastic, as I said. Okay, all the section is going to be fully plastic. Or number two, lateral torsional buckling, either elastic or inelastic. So we are going to have like these two different failure modes that might occur. Who is going to, what is the main factor for controlling this? You're going to find that next slides I'm going to talk about L-braced and how we can check whether that the failure mode of the beam is going to be by reaching MP or by lateral torsional buckling, whether elastically or inelastically. Okay. Okay, actually I was talking here about why this is 3.75 and this is 0.38. Already this is only like written note, so you can refer to it because already I have explained it in the previous slide. Okay, now let's go. Again, we are under the title of Bending Strength of Compact Shapes. Okay. For the Webb criterion is met by all standard I and C shapes listed in the manual for F yield less than or equal to 65 KSI. Therefore, in most cases, only flange ratio needs to be checked. Here we are talking about something that is important. Whips are going to be compact, okay, for shapes that is having F yield less than or equal to 65 KSI. Sometimes we need to check for the flanges, sometimes, okay. Built up welded I shapes, which is like girders and so on, can have non-compact or slender whips. Take care. I'm talking here about the hot rolled sections, okay, that you're going to find in the table, in the manual. But built up, okay, like blade girders or something like this, or built up sections. Remember that built up welded I shapes can have non-compact or slender. You need to check it. Most shapes will also satisfy flange requirements. I said here that flange requirements that you need to check, but you are going to find that most of the shapes, or most shapes are going to satisfy the flange requirements and will therefore be classified as compact. Okay, that's common. The non-compact shapes are identified in the dimensions and properties table. So you need to look to the dimensions and properties table from now on by considering a footnote F in order to see whether that your section is going to be non-compact or not. Okay, so the non-compact shapes are identified in the dimensions and properties table with a footnote F. Check this footnote whenever that you are designing your beam. Note that compression members have different criteria than flexural members, because in the previous chapter that we were talking about compression members, and I've mentioned that some shapes they might not be, like they might be slender, for example, but this is for compression members. For flexural members, maybe the section that was slender here for the compression, it is going to be compact here. So they are different. Take care. They are different. So the compression member sections for compression members are different than flexure members. Maybe it is compact for compression. So do not say that it was compact and when I was designing the column, this section. No. It might be compact for flexure, for example, but it is slender for compression. So do not be confused. As discussed in chapter 4, which is columns, shapes with slender compression elements are identified with footnote C. Okay, so we're going to find footnote F means that non-compact, as we said, and footnote C, this means that slender. Okay. Okay, this is very important notes for you when you are using the table, and it is related to the compactness and non-compactness and slenderness of the cross section. Okay, now I'm going to talk about something related to the braced length and unbraced length. Whenever we have a beam, okay, we are going to assume that the distance between the points that is bracing the compression flange, we are going to denote it with LB. Okay, so if we have a lateral support here for the compression flange, okay, we call it compression flange bracing. This means that the distance from this point to this point is going to be LB. We're going to denote it by X, as you can see. X means that compression flange is restrained. Okay, okay, let's go. Actually, this you can read it by yourself, but I'm going to explain it in a better way in the next figure, as you can see. This figure is the most important figure in today's video. Okay, so if you didn't understand anything before, okay, and if you are not going to understand anything after, it's not important. But this part is the most important part in the video for today. Okay, if you could understand the idea here, then flexural or beams or flexural strengths of beams in general is going to be very easy for you to be understood. Okay, the point is we are going to categorize the shapes, or we are going to categorize the failure modes based on the unbraced length. So we're going to put in the horizontal axis here, we're going to put LB, which is the unbraced length. And you understand now what is the meaning of unbraced length. It is the distance between the bracing points of the compression flange. And in the vertical axis, we are going to put the nominal moment. Okay? Well, then based on experiments, based on equations, based on formulas, whatever, we have obtained this curve, as you can see, very similar to the curve that we've discussed before regarding compression elements. Do you remember? And we are going to put different parts for the horizontal axis, okay? Different zones. The first part where that LB, the bracing length, is going to be small until reaching point called LP, then this distance is going to identify what we call it no instability here. If the cross section is here, this means that its nominal moment strength is going to be M plastic moment, which is going to be higher than M yield. We're not talking about M yield now. Commonly, whenever that you're talking about flexural members, you're not going to find M yield. M yield is in between actually, but it doesn't matter now. We need to put another type of limits. We are having the proportional limit, where that it is going to distinguish between two different types of lateral torsional buckling. The part between LP and LR, this zone on the horizontal axis, it gives us the inelastic lateral torsional buckling. You're going to find that the nominal moment is going to be less than M plastic, and it is gradually decreasing until it reaches a point here. This point is identified on the horizontal axis by LR, proportional limit. If LB is larger than LR, then the section is going to be slender. This means what? Full elastic lateral torsional buckling and no material yield or plasticity or plastic moment would occur. So if the element is having this unbraced length, this means that the cross section is going to buckle. LTB is going to be there, an elastic way, without any kind of yielding of any part of the material. However, if our section is having unbraced length between LP and LR, then it is going to have what we call it inelastic lateral torsional buckling. So what is the meaning of inelastic lateral torsional buckling? It means that part of the section may yield, which is the extreme fibers of the section, and other part buckles, and the other part buckles laterally. So it is like a combination between lateral torsional buckling and yielding. So it is something like a transition zone, as you can see it here. So inelastic lateral torsional buckling means part of the section may yield and other part buckles laterally. Extreme fibers yield, other parts buckles. Okay, other part buckles. Okay. And here MP, whereas the no instability, we are not concerned here with any kind of instability issues. There is no local buckling for the flange or web, nothing here. Full plastic moment will develop because material exceeded yield. Already we are exceeding the yield. We are in the M plastic. No kind of local buckling would take place here. Okay? This is what we call it the compact shape relation between LB and MN, okay, for our sections. And this is the failure modes that you're going to find for compact shapes. Again, we are having here reaching plastic limit, which is MP, or inelastic lateral torsional buckling from LP to LR, or elastic lateral torsional buckling. Okay, these are like the three different zones that we need to distinguish whenever that we are talking about the compact shapes. Okay, no M yield here. Okay, I mean that it is somewhere here, but we are not concerned with it. We're concerned with something else. MR, which is going to distinguish between elastic and inelastic lateral torsional buckling, and MP, which is going to give us the highest level of nominal moment strength of the cross section. Okay, please stop the video here, think and ponder over what I have explained regarding this figure, and try to understand it deeper. Okay, reflect upon it deeper, because really it's very important for you. Okay, now we are going to put some numerical values for the controlling parameters. So as usual, AISC is giving everything for us, or trying to make it easy for us to obtain LP, LR, MR, MP. We do not know how these controlling parameters are going to be calculated. So the point is, AISC is giving them for us in an easy way without thinking too much. But I want you to remember what is the significance of them, and I'm going to explain some points and some hints that is going to help you understanding the meaning of each of them. Okay, now for LB, it is the unbraced lens, as I said, and MN, it is the MP. If compact and sufficient lateral bracing is provided, means that from here to here, which is LB, is less than or equal to LP. Okay, so we are here, we are in this zone here. Okay, then what is LP? It is the plastic limit, how we can give it or numerically evaluate it. It is going to be 1.76 RY. Take care, we are talking about RY. The smallest radius of gyration, okay, RY. If I ask you here why we didn't use RX, because we are expecting what? Yes, lateral torsional buckling. So the behavior is going to be something like this. We are expecting the section to laterally move. So everything related to the radius of gyration, of the least radius of gyration around Y, going to be there. Okay, then LR, you're going this fantastic equation here, really nice equation. You're going to find everything is being put here. Okay, the point is, I want you to understand it deeper also. Whenever we are talking about LR, this means that proportional limit. So by default, you're going to find something that is grasping your eyes. For example, SX, elastic section modulus. Okay, this is number one. Number two, you are going to find F yield is always there in every part, but here F yield outside of any radicals. It's not like this, right? Then there is something called RTS. What is the RTS? It is this equation, IY times C warping over SX, elastic section modulus and warping constant, and the least moment of inertia. It makes sense, right? Why? Because we are differentiating between something that is going to be elastic lateral torsional or inelastic lateral torsional, right? So everything is making sense here. J, I'm going to explain about it in a minute. Here, this J means that torsional constant. Why we put this J here? Because we are expecting some lateral torsional buckling here, right? So we want something related to torsion. What is C here? Okay, so C, it is going to be 1 for doubly symmetric I shapes, or going to be this nice equation, which is having H node IY and warping constant. Also, it is related to the shape itself, right? So do not worry, it is going to be given in the table. Do not worry about this. So the point is that everything, in order to obtain LR, if you look to it, every single parameter, it makes sense that it is related to the shape, warping, torsion, elastic modulus, something like this. So this equation is really making sense for us to calculate LR. However, if you are going to look to LP, you're going to find that very simple. We're having only RY here. And we have something related to yield moment, the yield stress of the cross section. And RY, it is the least radius of gyration. That's right, because we have here we have inelastic lateral torsional buckling, and here we have something related to the MP. Right? Okay. Now MP, it is from the previous video. It is Zx times F yield, and MR, it is the proportional limit. It is going to have Sx times F yield, 0.7 of it. And this is MR. So we are expecting M yield to be here, for example. Okay. So this is like the definition of whatever that you are going to see, LP and LR. Then we put it on this shape, everything numerical, so that you can stop the video and look to it and understand what is the nominal strength for each case that you have. This area where that you're going to have your nominal moment strength is MP. This transition area, inelastic lateral torsional buckling, it is going to be, as you can see here, MP minus MR over times this fraction. Here MN, it is going to be FCR, as we are going to see, FCR times SX, where that FCR is going to be like this. It is very similar to the FCR. Do you remember the compression and so on of the critical buckling of compression members that we have discussed before? It is not the same here, but again, it is similar to it. We having these like terrific and nice parameters that we have explained, okay, a minute ago. Okay, so anyway, do not be overtaken or distracted with these so many parameters, okay? Do not worry about this. They are really simple and easy if you understood them only once, and after that you can find them from the tables. One thing that I want you to take care of, there is something here very interesting that has appeared, okay, especially in this part and this part. If you look to the equations, you're going to find CB, and also here there is CB. Actually, it is, I put it in red because maybe it was missed in the textbook or whatever, the picture that I have taken this graph from. So CB here. CB means that it is a factor that is taking into consideration the non-uniform moment or bending moment across the beam itself. If we have moment like this, it is different than moment like this. It is different than moment like this. It is different than moment like this. Okay? This means that we have contribution of loading condition. So the contribution of loading and bending and uniformity of bending is very important as well in the controlling or in the nominal strength of the nominal moment or the moment capacity of the section. The type and the pattern and the non-uniformity or the moment gradient is going to be important element for controlling or for the moment capacity of the whole section. Okay. However, in the part that is related to the plastic moment, we found only MP. It has nothing to do with the moment gradient. We do not care about what is the shape of the moment across the or along the element. Okay? Okay. Okay, we are almost 1 hour. I'm worried about this. But anyway, I'm going to finish within, I think, that 10 minutes or so. Okay, so now the definition of all of them, of all of this is like LB, we know unbraced length, IY, moment of inertia about the weak axis, and I mentioned why we're talking about weak axis. G, which is commonly used here, this is like G. Where is G? I'm sure that it is like written somewhere here. You're not allowed to, or I mean that you are not supposedly to remember or memorize this, okay? It is not the point to memorize anything here. You are going to find it or given to you in the manual, okay? So you are going to find that G, shear modulus of structural steel, it is constant. J, torsional constant. CW is going to be the warping constant. G, J, CW. Okay, it is defined in chapter 4. Okay, for the case of columns, you can go for them, but they are related to the shape, and the title are related to the torsional and warping constants and so on. The important thing that you need to take care of is CB, which is a factor that counting for non-uniform bending. We call it the bending or the moment gradient within the unbrazed length. Okay, this is going to be controlling parameter for the moment capacity. RTS squared, it is related to three main parameters: IY, C warping, which is the warping constant, and elastic section modulus. See whether we take it 1, or with this equation for channels and for I shapes we take it only 1, and you can find them in these equations in AISC. H node, distance between flange centroids, D minus TF. Okay, this is what you are going to do. The summary of the nominal flexural strength for compact section. I'm talking about compact section. Remember that we are talking about compact sections. Okay. The nominal bending strength for compact I and C shaped sections can be summarized as follows. So we are having three different zones. If our brazed length less than LP, or between LP and LR, or larger than LR. So we have like three zones: zone 1, zone 2, zone 3. This is going to be in plastic. Here it is going to be inelastic lateral torsional buckling. Here it is going to be elastic lateral torsional buckling. In the first zone, MN simply going to be MP. In the second zone, MN, which is the nominal flexural strength, it is going to be CB, which is taking into consideration the non-uniform moment. Okay, we call it non-uniform moment factor, times MP, plastic moment, times MP minus 0.7 F field SX, this is elastic modulus, okay, times this value, which is LB minus LP over LR minus LP. Okay, it is like the ratio where exactly our LP or LB is in between LR and LP. And it should always be limited, upper limit, with MP. If our L unbrazed length is going to be larger than LR, the proportional limit, then our nominal moment flexure strength is going to be FCR times SX, and it should always be less than MP. This FCR is going to be also CB is there, the contribution of the moment gradient. This means that we need to take care of the moment gradient across or along our unbrazed length. Then it equals to by squared CB by squared E over LB times RTS squared times the radical of this nice terms here. Okay. Okay, now I think that you are waiting now for example. We have discussed much regarding parameters. Let's go and have an example now. Okay, first of all, this example is related to determining the flexure strength of a wide flange 14 by 68 of A242 steels. Okay, this is a little bit new for us. We didn't use it before. Okay, so for three different cases, we're going to talk about three different cases here. The first case is our flange is continuously supported, so continuous lateral support. Okay. The second case, if we have unbrazed length of 20 feet with CB equal to 1, so the moment gradient is no contribution here, and the unbrazed length is 30 feet with CB equal to 1. Okay, so we have like three different cases. Let's check what is the flexure strength for these three cases. first of all, for this type of steel, we need to know what is F yield here, because F yield is like we use it numerously, right? We need F yield here, right? And we need it at least for the calculations, okay? So we need to know what is F yield for A242. So we are going to visit table 2-3 in part 2 of the manual. Please stop the video and go to the manual part 2 and check this table. Okay. So the yield stress for this is a function of the flange thickness, which for this shape is 0.72. This is from the dimension and properties table. For our cross section, you can find that the thickness of the flange is 0.72. Then when we go to this table here, this is table 2-3. Okay, already we have explained before. You are going to find A242 here. I magnified it here. Then you're going to find that F yield, this is F yield, right? Here, this is F yield here, this column. You're going to find different types of F yield, right? And you're going to find this one, which is like this, 50, okay, with the superscript I. This means that for shapes with flange thickness less sorry for this, with a flange thickness less than or equal to 1.5 inch only, because these values are related to the flange length. So we have different values, shapes with thickness greater or greater than and less than, and here less than. Our case, we are having 0.72 flange thickness. This means that F yield for our case is going to be 50 KSI. 50 KSI. Okay, so this is 50 KSI. This corresponds to footnote I. As I said, this is I here. Maybe it's not very clear, but you can find it in the table. Okay. Next, determine whether this shape is compact, non-compact, or slender, right? We want to know what this shape is. It is compact. So now, for the steel, we know that F yield equal to 50 KSI. Now for this shape, what is the type of this shape, compact or not? Then we're going to check everything. We're going to check the flange and the width. For the flange, B flange over 2TF, it is going to be 6.97 from part 1 of the manual, dimension and properties table. Please stop the video and check this by yourself. Then our limit for the upper limit for the compact section is 0.38 radical of E over F yield, right? So if we know E for the steel, 29,000, KSI, F yield is 50, already we have taken it before. So we have 9.15, which is larger than 6.97. This means that our flange is compact. Well, should we go and check for the width? The answer is no. The width is compact for all shapes in the manual for F yield less than 65 KSI. Okay, so now less than, we're talking about all for F yield less than 65. Our case is 50 KSI. Then this shape is compact because its width is compact and its flange is compact as well. So the shape is compact. Okay. This determination could also be made by observing that there is no footnote in the dimensions and properties table to indicate that the shape is not compact. That's also a very smart way. Check it in the dimension and properties table. You're going to find this shape W14 by 68. It doesn't have any footnote related to the non-compactness. This means that by default it is compact. Okay, now let's go to the first requirement, which is A. The beam is compact and laterally supported, means that continuous lateral support. So the nominal flexure strength is going to be, without thinking too much, our LB, okay, our braced length is almost like 0. So in the table we are here, we are in this point, and the figure we are here, less than LP. So this means that our nominal strength is going to be MP, and it equals to F yield times ZX. F yield 50, ZX 115. This can be obtained from the tables. Okay, check this plastic modulus. Then we have, this is M plastic for us. This is M plastic for this cross section. Then the design strength is going to be, for the case of LRFD, we will multiply by 9.9 times M plastic. Then this is the LRFD, the design strength. If we're going to talk about ASD, then the allowable moment strength is going to be MN over 1.67, which is going to give us 288 foot kips. This is the first requirement. Very easy and simple. We are here in the plastic range. Let's go to the next part, which is requirement B, where that LB equal to 20 feet and CB equal to 1. So first of all, we want to check where is LP and LR. Where is, or what are our limits? We want to know where is LP and where is LR. So we need to calculate them. Okay, so strongly recommend for you, stop the video here and calculate LP by yourself and LR by yourself, please. Everything is written in front of you, but I strongly recommend for you to calculate it by your hand. Okay, because really it is simple to go and follow here, but I want you to check everything by yourself. Okay, so LP is going to be 1.76 RYE over F yield. This is, everything is given, even RY. We can, radius of gyration from the table, we can obtain it, 8.6 feet. Okay, and for the LR, it is this fantastic equation. So you need to stop the video and check every point here. Every single parameter is given for you in very long equation, as you can see. I'm going only to highlight that the important thing, RTS, and instead of calculation, you can find RTS can also be found in the dimension and properties table. So no need to calculate this part. Okay, you can find it in dimension and properties table. We're going to find it for our shape. It is going to be 2.8. Okay, that's number one. H node is also given in the dimension and properties table. Okay, it is given 13.3. Please check them. Go and check. For a doubly symmetric I shape, C equal to 1, as we said before, from equation F2-8-A. Then LR can be calculated from this long equation simply by substitution. You're going to find that you are 29. So we are LP, previously LP, it was 8.6. This is 8.6. LR, it is 29.28. Our section or our length is what? We are here because we are 20 feet, right? So we are in between. What is the mode failure here? It is going to be inelastic lateral torsional buckling. Inelastic lateral torsional buckling. Okay, that's very important. This is the mode failure that we are expecting because of the unbraced length of 20. So our case is here, inelastic lateral torsional buckling. Based on that, we are going to use this equation. Let's go back here. Yes, the second equation. We are here. We're going to use this nominal equation in order to obtain the nominal flexure strength. Okay, so we are going to substitute everything in this equation. CB, as it is given already 1 for us. MP from the previous calculation, previous step, and then MP F yield 50 SX from the dimension and properties table. LB, LP, LR, LP, everything is known for us. And it should always be capped with MP. Plastic moment should be the upper limit. We found that here we can obtain 381, which is less than MP, which is 479. Okay, from equation part A. Then the design strength for LRFD, multiply this value by 0.9 and for ASD, multiply the nominal moment, the same nominal moment here, multiply it by 0.6, or like divide by 1.67. It gives you the allowable moment strengths for LRFD and for the design strengths of for ASD, and for design strengths for LRFD is given for us here. Okay, now let's go to the last part, which is related to part C. LB equal to 30 feet and CB equal to 1. By looking, we have LB is larger than LR. From where we got LR? Previously calculated. This is LR. 29. It's not going to be changed. It is going to be fixed. So we are here. We are here. Elastic lateral torsional buckling. Then we need to use this equation of FCR, right? Let's go back to our roadmap here. Yes, we are here. So this is the case LB larger than LR, then MN equal to FCR times SX, and should be capped with MP and FCR equal to this nice equation here. Okay, and let's go. Okay, we are here. So FCR can be calculated easily. CB, it is 1. Pi squared E, known for us. LB, it is 30. RTS, already calculated before. J, C, SX, H node, they are known from us, whether from the tables or that we have calculated before. LB is 30. RTS is already known. Substitute all of this in the equation and obtain the output, which is 33.9. This is FCR. Then multiply it by elastic section modulus. We're talking about elastic section modulus, not plastic. Take care. So then you are going to obtain the nominal flexure strengths. It should be capped with the M plastic always. It should not exceed it, of course. Then we are okay. 229 less than 479. Based on this, we are going to find that LRFD solution 0.9 times 291, it is 262, and here for ASD it is 175. Okay, I'm going to recap only. Take care of these values. So if our section A, our LRFD was 431, we are here, MP. After that, in section B, okay, we found that our LB, it was the unbraced length 20 feet. We found that we ended up with LRFD 343. We are here, not MP, right? Less. And then the last case, when LB equal to 30, we found that our LRFD is 262. We are here. So we were here in A, we were here in B, we are here in C. This gives to you an important understanding of the contribution of the unbraced length. If we have small unbraced length, then our capacity is almost, it was like 400 something, right? 400, I'm not sure, 400 something. Here, it was 300 something, right? Here, we're talking about 200 something, 262 or something. Can you imagine? By controlling the bracing length, you are controlling the nominal flexure or the design flexure strength of your sections. Okay. I hope by the end of this example you understand really what is the meaning of nominal strengths of compact sections for beams. And please try to stop the video at any time and think about every point that I have explained. Try to work out this example alone without looking to the video, without watching the video, and try to visit the manual and the specifications, okay, at the specific points that I have mentioned here, and try to work it by yourself. It's very important for you to get familiar with what I have explained. Okay, so this brings us to the end of this video. I hope that you have understood everything that I've explained. Please remember that this slide is very important for you. Okay, very important. Try to focus on this graph, and also the definitions. Yes, this one or this slide is very important for you. Try to focus on understanding the meaning of compact, non-compact, and slender sections. And finally, remember the global and local instability issues that I have explained. Thank you very much, and see you in the next video.